Hello students. By now we know that how does the atomic radius, ionic radius and ionization enthalpy vary in a period and in a group. We will be discussing about trends shown by few more properties like electron gain enthalpy, electronegativity and chemical reactivity. After this discussion, you will be able to explain the meaning of these terms and also relate with the factors affecting electron gain enthalpy and electronegativity of an element. Discuss the periodic trends in electron gain enthalpy, electronegativity, and chemical properties. Relate electron gain enthalpy with non-metallic character. Use scientific vocabulary appropriately to communicate ideas related to certain important properties of atoms like electron gain enthalpy and electronegativity. We know that energy is required to remove the outermost electron from an atom because this electron is experiencing nuclear attraction. Similarly, if electron is added to the nucleus, this will also experience attraction by the nucleus. When it experiences attraction, some energy is released. This is termed as electron gain enthalpy. It is defined as the energy released when an extra electron is added to a neutral isolated gaseous atom to form the gaseous negative ion, that is anion. It is denoted by delta Eg capital H. It is a measure of the ease with which an extra electron can be added to the atom and how strongly it is bonded to the nucleus. It is measured in electron volts per atom or kilojoules per mole. Depending on the element, the process of adding an electron to the atom can be either endothermic or exothermic. For many elements, energy is released when an electron is added to the atom and the electron gain enthalpy is negative. For example, group 17 elements, that is the halogens, have very high negative electron gain enthalpies because they can attain stable noble gas electronic configurations by gaining an electron. On the other hand, noble gases have large positive electron gain enthalpies because the electron has to enter the next higher principal quantum level, leading to a very unstable electronic configuration. It may be noted that electron gain enthalpies have large negative values towards the upper right of the periodic table preceding the noble gases. Students, do you know how electron gain enthalpy changes in a period and in a group of the periodic table? Let us discuss. The variation in electron gain enthalpies of elements is less systematic than for ionization enthalpies. As we move down a group, we expect electron gain enthalpy to become less negative because the atomic size increases, and with increase in atomic size, the attraction of the nucleus for the incoming electron decreases. Hence, the electron gain enthalpy becomes less negative. However, there are few exceptions like the electron gain enthalpy of oxygen and fluorine is less negative than that of the succeeding element. Let us discuss why does this happen. This is because when an electron is added to oxygen or fluorine, the added electron goes to the smaller quantum level, that is n equals 2, and suffers significant repulsion from the other electrons present in this level. For n equals 3 quantum level, for sulfur or chlorine, the added electron occupies a larger region of space and the electron-electron repulsion is much less. Now, let us discuss trend shown by electron gain enthalpy along a period. As we move across a period from left to right, the atomic size decreases and the nuclear charge increases. That is, effective nuclear charge increases. Both these factors tend to increase the attraction by the nucleus for the incoming electron. Hence, electron gain enthalpy is expected to become more and more negative as we move from left to right in a period. But the electron gain enthalpy of noble gases is positive. Students, can you tell why is it positive? The atoms of these elements have completely filled subshell. As a result, there is no room in their valence orbitals and the additional electron has to be placed in an orbital of next higher shell. As a result, energy has to be supplied to add on additional electrons. Let us discuss another trend followed by another property called electronegativity. But before that, we need to understand what is electronegativity. In case of bond between two different atoms, the respective pull on the electrons of shared pair are not equal. One of the atom attracts the shared pair more strongly than the other. This atom is said to be more electronegative. So, electronegativity may be defined as the tendency of an atom to attract the shared pair of electrons of a covalent bond towards itself. The electronegativity of any given element is not constant. It varies depending on the element to which it is bonded, though it is not a measurable quantity. Electronegativity of elements are available in literature on different scales. However, the most widely used is the Pauling scale. In the periodic table, fluorine with the value of 4 is the most electronegative element, whereas cesium with the value of 0.7 is the least electronegative element. Electronegativity generally increases across a period from left to right, say from lithium to fluorine, and decreases down a group, let's say from fluorine to astatine, in the periodic table. This trend is similar to that of ionization enthalpy. It is clearly relatable to metallic character as well. As the electronegativity increases, the non-metallic character increases. As the electronegativity decreases, the metallic character increases. Fluorine, with the highest electronegativity of 4, is the most non-metallic element, and cesium, with the lowest electronegativity of 0.7, is the most metallic element. Till now, we have observed and understood various characteristics of an atom. They follow a certain trend in the periodic table, and hence, consequently, there is a trend in chemical properties too. Students, now we shall study the periodicity of the valence state shown by elements and the anomalous properties of the second period elements. The valence is the most characteristic property of the elements and can be understood in terms of their electronic configurations. The valence of representative elements is usually, though not necessarily, equal to the number of electrons in the outermost orbitals or equal to 8 minus the number of outermost electrons as shown. Nowadays, the term oxidation state is frequently used. Oxidation state of an element in a particular compound can be defined as the charge acquired by its atom on the basis of electronegative consideration from other atoms in the molecule. This can be understood better by taking example of sodium oxide. Oxygen is highly electronegative than sodium atom, so oxygen will attract 2 electrons from each sodium atom, showing -2 oxidation state, and sodium will have +1 oxidation state. Thus, we see that the oxidation state of the element represents the charge possessed by an atom due to loss or gain of electrons, which is due to the electronegativity difference between the combining atoms in the molecule. The oxidation number in a group remains constant as the elements have same valence shell configuration, whereas oxidation number of the elements first increase and then decreases across a period. Transition and inner transition elements exhibit variable oxidation states. The second period elements show differences in some properties from the other elements in their respective groups and similarities with the elements present diagonally across them. For example, lithium, unlike other alkali metals, form compounds with pronounced covalent character, whereas the other members of these groups predominantly form ionic compounds. Behavior of lithium is found to be more similar to magnesium, which is the second element of the following group. Students, try recalling the design of the periodic table. You will notice that these elements are present at a diagonal position. Hence, this behavioral resemblance is named as diagonal relationship. This anomalous behavior of second period elements is due to smaller size, larger charge to radius ratio, and higher electronegativity of these elements as compared to the other members in the group. The availability of lesser number of orbitals and the peculiarity of their bonding capabilities also contribute to the anomalous behavior of second period elements. Because of the absence of d orbitals, these elements cannot form more than 4 bonds. Simply because they have only 4 valence orbitals, which are 1 2s and 3 2p orbitals. That is the reason Bf4 negative is possible and Bf6 3 negative is not possible, while AlF6 3 negative is formed. By now, we very well understand that all chemical and physical properties are a function of the electronic configuration of elements. Let us try to establish relationships between these fundamental properties of elements with their chemical reactivity. There is a high chemical reactivity at the two extremes and the lowest in the center of the periodic table. Thus, the maximum chemical reactivity at the extreme left, that is among alkali metals, is exhibited by the loss of an electron leading to the formation of a cation, and at the extreme right, that is among halogens, is shown by the gain of an electron forming an anion. This we can relate to low ionization enthalpy on left of the periodic table and high negative electron gain enthalpy at extreme right, not noble gases, but for halogens. Consequently, high metallic character on the left and non-metallic on the right of the periodic table. A very interesting way to show chemical reactivity of an element is by its reaction with oxygen to form oxides. The normal oxide formed by the element on extreme left is most basic, for example, sodium oxide, whereas that formed by the element on extreme right is the most acidic, for example, dichlorine heptaoxide, that is Cl2O7. Oxides of elements in the center are amphoteric, like aluminium oxide, or neutral, for example, CO. Amphoteric oxides behave as acidic with bases and as basic with acids, whereas neutral oxides have no acidic or basic properties. Students, since you are already familiar with this concept, let us reinforce it by taking this question. How will you show that Na2O is basic oxide and Cl2O7 is an acidic oxide? You can very easily explain this by showing its reaction with water. Have a look at the reactions. Sodium oxide forms sodium hydroxide, a strong alkali, and Cl2O7 forms perchloric acid. We can confirm basic and acidic nature by using litmus test. Sodium oxide will change color of red litmus paper to blue, indicating its basic nature, and perchloric acid will change color of blue litmus paper to red, indicating its acidic nature. Thus, from the discussion till now, we conclude that electron gain enthalpies in general become more negative across a period and less negative down a group. Electronegativity increases from left to right in a period while decreases down the group like ionization enthalpy. There is some periodicity in valence. For example, among representative elements, the valence is either equal to the number of electrons in the outermost orbitals or 8 minus this number. Chemical reactivity is highest at the two extremes of a period and is lowest in the center. The reactivity on the left extreme of a period is because of low ionization enthalpy, that is the ease with which the elements lose electron. Oxides formed of the elements on the left are basic and of the elements on the right are acidic in nature. Oxides of elements in the center are amphoteric or neutral. Students, here are a few questions for you to test yourself. Question 1. Which of the following pairs of elements would have a more negative electron gain enthalpy and why? Oxygen or fluorine? Fluorine or chlorine? Question 2. Considering the elements boron, carbon, nitrogen, fluorine and silicon, what is the correct order of their electron gain enthalpy? Question 3. How would you react to the statement that the electron negativity of nitrogen on Pauling scale is 3 in all the nitrogen compounds? Students, keep practicing and keep learning. Have a nice day. Thank you.